Welcome back to our space segment discussion. We stopped last at this particular slide which talks about reaction wheel, and this reaction wheel we are using to generate some stiffness. That means we run a wheel with a motor, and its speed, as we increase, the stiffness of the axis is adjusted. So we have to continue to run this motor. So disturbing torque can be adjusted and further disturbances may come. So that is slightly difficult. So what is done is we have to stop this motor and let this torque be taken over by something else and get into the natural phenomena. So that is done by some technique is changeover. So when the maximum speed of the reaction wheel is reached and still more torque is required, then the thrusters are used. Thrusters are just the principle is just like a rocket propulsion. So this changeover from the reaction wheel to the thruster is done gradually. As you increase the thruster thrust, the reaction wheel speed is reduced gradually, and at some point of time reaction wheel speed will be 0 and thruster has achieved that particular thrust, and then thruster can be switched off. The thrust is already given. So this enough torque to cancel the disturbing torque, the thrusters are switched off and reaction wheel can now take over for further correction in future. This reaction wheel is set to 0 now. So this is called momentum dumping in space technique. Okay, what is a thruster? Let us get into a very brief description of that. It produces force by expelling materials through a nozzle, and that force obviously is equal to F is equal to gravitational acceleration, then something called specific impulse and mass of the fuel per unit time. So the amount of fuel that is required, the mass is, you can side change that, is equal to m is equal to force into the time divided by gravitational acceleration and the specific impulse, that is in kg. Now this force is given at the nozzle point, so the torque is generated. It depends on from the satellite center or body of this center body of the satellite center point to that particular nozzle, the length. So this force into this length will be torque. Torque is F into L, where L is the length from the center of the satellite to the satellite body to the nozzle. That is the thruster. And how it is done? Thrusters have capability to generate torque of the order of few newtons to tens of newtons, and very small thrust if it is required, a fraction of a newton, that can be generated by variable duty cycle of expelling the fuel or the on off pulsing of the thrusters, and with approximate calculation could be with 1 meter length and the force of 10 to the power minus 4 to 10 to the power minus 1 newton, a torque of 10 to the power minus 4 to 10 to the power minus 1 newton meter can be realized. Simple. Now there is a brief block diagram of that. That is, the fuel is there in a tank and compressed nitrogen is pressing the fuel out, that goes through a filter and then it gets into a valve which is controlled how much fuel has to be expelled, and then there is a combustion chamber where this fuel is mixed with a catalyst and oxidizer and it goes out to the nozzle. Generally this fuel is hydrazine, a name chemical name is hydrazine, the chemical compound is N2H4 and the catalyst is iridium and oxidizer is nitrogen tetroxide. This is a typical arrangement. There may be many other combinations. These are falling under the propulsion system. We won't discuss much about this. These are all chemicals things, just for brief information for you. Then let us look at the orbit. The satellite structure is also adjusted sometimes. Like just now we have talked about the gyroscopic stiffness that can be generated. The satellite body itself could be a cylindrical body and it can be moved at a rate of 300 to 1000 rpm. If you move the body axis, the axis of the cylinder will be stiff. So this is a way of keeping stiff body. But then you see there is a problem, that if there is a antenna with parabolic antenna, the focused antenna in one direction, and if you rotate the satellite, the antenna will not be moving, will not be looking at the earth or surface area, it will be moving all around. So therefore this has to be adjusted. How it is adjusted? Then you put a slip ring around the body of the satellite. Body of the satellite contains the solar panels, cylindrical portion has the solar panels that are spun, and the rest of the body is dispun by a slip ring, and that whole satellite structure is fitted to the slip ring. This is a very simple arrangement, and this is called spin stabilized satellites. Initial satellites, if you remember in our first lectures, that is, we have shown you the Intelsat 1, which is a satellite of very small weight, and it was launched in 1965. Those earlier days, the spin stabilized satellites are very popular. Even now there are some spin stabilized satellites are there. The disadvantage in this, you can see that only half portion of the solar panel is seeing the sun. Another disadvantage is, of course, the satellite structure which contains the antenna has to be mounted on a dispun arrangement with the satellite. So these two difficulties are to be recovered. Now in this spin rate can be decayed with time, and periodic corrections may be necessary. The north-south station keeping is done by the thrusters which are parallel to the spin axis, that is, you can see the toppling of that, and east to west station keeping is done which is perpendicular to the spin axis. Okay. And then spin stabilized satellites have the advantage of simplicity, but has the problem of solar panel size is more, and half of the portion of the solar panel does not see the sun at a time. So to generate this stiffness, we can think of the other technique is inside the satellite body, 3 momentum wheels in 3 different perpendicular axes can be used, and they will maintain the 3 axis stabilization. The rest of the structure of the satellite is fixed with the 3 axes of the momentum wheel using the slip ring technique itself. An advantage is easy orientation. Satellite structure can be rectangular shape or any other shape, and solar panel could be made of optimal size, always oriented toward the sun. Antennas can be pointed to the service area. So nowadays most of the satellites are this 3 axis body stabilized system. That is the present form of the satellite. So this is a very brief description of what we have seen in attitude and orbit control system. So let us now change over to the other subsystem, which of more interest to us is telemetry, tracking and command, in short TTC. Its function, let us try to recollect, that is to monitor the subsystem health and status parameter, that is telemetry, to support detecting the orbital parameter, the tracking, and to provide the source for the station to the track satellite, obviously that is also tracking, and to receive and execute commands to perform the required function, that is the command. Now let us see the telemetry. Primarily telemetry of the subsystem that monitors the health and status of the satellite bus as well as payload. Each of the subsystems has to be monitored how it is functioning. But in some cases of remote sensing satellites, telemetry term is also used for transmitting observed data collected from the sensors which are looking towards the earth, planet or star to the ground system. So the data collection is outside the satellite, that is also called telemetry. But in this case our communication satellites will be confining ourselves to the health monitoring and status monitoring of the bus and payload, that we will call telemetry. Obviously the data requirement, the volume of data will be much smaller compared to the sensing data from other objects. So monitoring parameter could be any of the following, like circuit voltage, current of the circuit, the temperature, the pressure, the status of a switch, the wheel speed, or like that many other things. The analog parameters obviously are transmitted directly by subcarrier modulation or it is more popular nowadays, is to digitize this analog parameter, encode it, format it, modulate and transmit to the ground station, just like any other RF transmission. And a short block diagram of this concept is, say, analog sensors are there, you have A to D converters, and then the digital data comes from the digital sensors. All these data from analog converted to digital, as well as digital sensors data are coded, formatted, and modulation and transmission is done. Now, this coding and formatting is generally done in the form of blocks or frames. So, the frames will be having a header which says this is the beginning of the frame, it is called frame synchronization bits, and then you can have telemetry words like TM1, TM2, TM3, and then there may be error correction code like error detection and correction code like CRC code, etc. So, generally this is a form of a telemetry frame. Now, since the volume of data is very low, the bit rates are also low, obviously of the order of 1 kilobit to 10 kilobits per second. This is what generally this telemetry is done. Now, telecommand, in short, it should be robust to avoid wrong or missed command. You cannot give a wrong command to that. So, therefore, different types of commands are defined. What should be the possibility of error that can be tolerated by a standards body, international standard body called Consultative Committee on Space Data Systems, CCSDS, and certain performance criteria they have proposed. They have given certain modes, like emergency mode is A, and where the block size of telecommand block size is about 100 bytes, 0.1 KB, this B for bytes, and the error on this code word is of the order of 10 to the power -3, that is tolerated. Undetected can be 10 to the power -9. The B mode is command mode, which is a slightly larger block size. The code error rate as well as the undetected code rate are same, whereas in case of file transfer or human support system is mode C and D, which is the error rate is and the undetected error rate is much higher. That can be adjusted by higher layer of protocol that will improve the undetected error rate. But in case of emergency and telecommand, actual command, mode A and mode B, your code error rate and undetected error rate is quite stringent. Now, telecommand should be robust to avoid wrong or missed command. And so, in addition to the error control, which is forward error correction or any other error control that can be used, there are other standard techniques which are used are repeat the command itself, and also a echo. That means, whatever command has gone, the satellite will return it back to the ground station, and ground station checks whether he has got back the what was sent, he has got back that one. So, you make sure that whole thing is correctly received by the satellite. So, there is a frame format for the telecommand also. It starts with the sync, just like telemetry, the frame at the beginning, sync word, and then the address of the command and control, then command word 1, command word 1 repeat, command word 2, command word 2 repeat, etc., and at the end of error check, similar to telemetry format. But in all this process, you just see the frame beginning is to be identified properly. Then only you can identify all other bits, including the error check bits. So, identifying the sync bit is bits is a very important criteria for us. And then the command is gone. To execute the command, a separate command is transmitted after making sure that command which was sent is received correctly by the earlier method what I described. So, three types of command executions are used. One is direct execution, as soon as command is gone and execute immediately. Second is the validate the command and then execute, and third is you send the command and it will get executed after some time based on certain event if it is happening. So, these three types of executions are used. But let us try to concentrate a little more on this synchronization word, which is common to telemetry frames as well as telecommand frames. Now, in this synchronization word, two properties characterize the code word length for the channel with high error. These are the missed detection probability PM, when errors occur in the code word itself, that is detection is missed, that is sync word has certain error, so the sync word itself is missed. So, that is one problem. You can realize what is happening, that is if the sync word is not detected, the whole frame is lost. So, if there is a error in the sync word itself, so you miss the sync word. So, what is that probability? It will be based on what is the error probability that is happening on the sync word, and the probability of misdetection can be calculated based on that. And in the actual command word or telemetry words, if there is a pattern which looks like sync word, that will be a false alarm. That will be starting point, and you will try to detect that as a beginning of the frame, then you will get into the wrong data detection. So, there are two things, missed detection and false alarm detection. When error in the data bits makes a word look like a sync word. So, these two has to be seen carefully. Missed detection, that is in the sync word itself there is a error, so you miss the detection itself, and another is in the data area there is a error which makes it look like sync. Generally, sync words are selected such that it does not in the data area a similar pattern does not appear. That is another aspect, but let us look at these two things. So, how it is detected? Sync word, how it is detected? Let us see first. Receiver correlates the received data, received word, with a locally generated, because it is known at the satellite also it is known what is the sync pattern. So, locally generated word, it should give a good autocorrelation. Let us say there is a shift register in which the receive pattern is received and is getting shifted bit by bit, and there is a locally generated stored pattern which is the expected pattern which is stored in a register. Now, these two are compared in a modulo 2 comparison. These two patterns are compared, and if there is a mismatch, there is a residual error, and this error level sometimes we tolerate some error level. So, this error level is compared with a threshold error. I can tolerate 1 error, I can tolerate 2 error, I can tolerate k errors. So, with this error threshold is compared and the detected pulse is generated. So, k could be 0, in that case you are not tolerating any error. So, based on this, let us frame a equation or expression, probability of misdetection, that is for a n bit word, if assume that sync word is of n bit duration. So, n bit word and bit error rate of probability p, small p, and when the system can accept equal to or more than k bit of error, can tolerate k bit of error, k could be 0, 1, 2, 3, it depends on the system, then the probability of misdetection or detection miss is expressed as sum of I is equal to k plus 1 to n, and then the binomial of n I p to the power I 1 minus p to the power n minus I. These you must be knowing, it is already known to you, this type of expressions. So, based on n and the probability, that is the sync bit size and the probability of error BER, and what you have decided about the k, that is how many bits you can tolerate, the probability of misdetection can be calculated. Similarly, for probability of false detection or false alarm is also expressed as p of fa, the sum of I is equal to 0 to k, that is how many you can tolerate, and then n I to the power by to the power n. Now, I give you a problem, you solve it. As the k increases, that is your tolerance of error increases, what will happen to probability of misdetection and probability of false alarm? Whether they will increase or they will decrease. When the, I repeat, when the tolerance of error increases, k increases, what will happen? PM will increase or decrease, PFA, that is probability of false alarm, will increase or decrease. Its problem is left to you. Okay. Let us go into some of the more descriptive detail, that is the allotted frequency, uplink frequency, which is for telecommand, is in S band, that is 2.025 gigahertz to 2.120 gigahertz. In terms of megahertz, it is 2025 to 2120 megahertz, and downlink frequency, which is telemetry, is 2200 to 2300 megahertz. You can see it is only 100 megahertz bandwidth available, and that is allotted worldwide. So it's very small bandwidth for so many satellites which are operating. So these frequencies are used only during the orbit placement and in case of emergency. Normally telemetry and telecommand is done through the communication channel, which is generally in C band or Ku band or Ka band. So telemetry and telecommand is done through communication payload band. Now in case of a problem, telemetry telecommands are emergency type of thing sometimes. So in case of this power level of that telecommand or telemetry carriers in the communication band is reduced below certain threshold level, that is, if the power level of TC carrier level is monitored, and if it is below certain threshold, then the transmitter receiver will be switched on, switched over to the emergency band, which is listed above, that is in S band. So this is generally done by the most of the receiver. There is the other part, which is tracking. To track the satellite from the ground, the look angle and range need to be found out. Look angle for tracking is found with the help of a separate beacon signal transmitted by the satellite. We have seen for orbit control, from the ground we have transmitted a signal, and at the satellite we are trying to look at that ground signal source. Similarly, satellite can transmit a signal, and an antenna can be pointing to that signal and adjust and find out what is the azimuth and elevation angle of the antenna. So look angle can be found from the beacon signal from the satellite. It is called beacon signal, and this is generally the telemetry carrier. And ground station uses tracking to determine the look angle precisely, and thus you can find out the angular position of the satellite. But what about the range, which is very critical to us? That is, it will give us certain delay of sending some signal from ground to satellite or satellite to ground. We will see in our TDMA discussion that one, the effect of that. But we have to track it. So we have to find out the range. How do you do it? A range or distance to the satellite from the station is found by measuring round trip delay of a signal. That signal could be a tone, that is pure single frequency, or a code. A tone is sent from the ground station, is received by the satellite TTC subsystem, and retransmitted back to the ground. So whatever a tone is sent, it is sent back to the ground. You can measure the phase delay, that is delay of sending, delay from the time of sending to the reception, and you can find out the delay, and from the delay, assuming that the signal is traveling at the velocity of light, electromagnetic wave is traveling at the velocity of light. So it is, you can find out the total path it has traveled, divide by 2, because it has gone up and down. So divide by 2 will give you the range. It is very simple. But then you are sending a tone. Let us see, 2 times, if r is the range, so 2 times of r is many times that lambda has gone once it has reached satellite and has come back. So there will be many waves n times the lambda and a fraction of the lambda. That is what you will be receiving. So that phase difference will be n times lambda and a fraction of a lambda. It can be called as a phi by 360, that fraction. Lambda is the wavelength, which is c by f. Range is r, and number of full cycle is n, and the phase difference, phase delay difference is phi, velocity of light is c, frequency is f. You see in this equation, the unknown thing is this n. You do not know how many cycles it has passed. The fraction you can measure, but unknown thing you cannot measure, which is n. That is the ambiguity. To remove this ambiguity of number of full cycles it has passed, we can send a signal with such a low wavelength, such a large wavelength, such a low tone, low frequency, very low frequency, so that in one wavelength itself, one wavelength itself will be more than the range, 2 times range delay. which in case of, you can calculate, in case of 2 times of geo range, which is 36,000 kilometer into 2, what could be the tone frequency? It will be less than 10 hertz. It will be of the order of 4 hertz or so. So it's a very small thing. There is another issue, with what accuracy you can measure, that is, let's call it delta R. Accuracy will be the phase accuracy with which you are measuring based on your measuring instrument by 360 and into lambda, that is C by F. So delta R is the accuracy in the range measurement and delta phi is the accuracy in phase measurement. To make the delta R small, to make this equation delta R small, the F has to go high. So we have two contradicting requirement. One is low frequency tone that will remove the full cycle ambiguity, and high frequency tone to improve the range accuracy. To remove the ambiguity, the number of full cycles passed, as well as achieve better range accuracy, 2 tones are used then for tracking. There is one is higher and one is lower frequency. So lower frequency tone recovers ambiguity, higher frequency tone gives accuracy. This distance ambiguity will be half of the wavelength as the signal travels the distance 2 times upward and downward, of course. But then much more precise ranging can be done through a spread spectrum technique. It is based on a correlation of transmitted code with the received one. Autocorrelation is of a signal. Xt is defined as it is autocorrelation function Rxt tau is integration of 0 to minus infinity to plus infinity xt and xt plus tau d tau. Now you know that what we'll do, today the time is not there much, so we'll stop at this point and we'll continue our discussion in the next class. That will be continuing the tracking. Thank you very much.